Hey everybody, Victoria and Corey here. We are the Professor's Du Bois, and today we're going to be introducing the concept of gases.
Alright, so gases are just a state of matter. We've got solids, liquids, and gases. Now with gases, the distance is rather large compared to solids and liquids between the molecules, and there's less interaction. The movement is in all directions, and it's constant, and we have a new measurement we can do with gases that we cannot do with liquids or solids, and that's we can measure pressure. And this is based on an amount of force per an amount of area.
So the variables that we are using with gases will be volume, and we usually use liters for that, temperature, and for all of your gases calculations, you're going to want to use Kelvin for the temperature. We're also going to be using moles again, and pressure, our new unit. And we use pressure in various different units. We use atmospheric pressure is in 1 atm, so that's kind of where that comes from, atmospheres. And millimeters of mercury, psi, which is pounds per square inch, kilopascals, bar. There's all kinds of different pressure units we can use.
So one way we can measure atmospheric pressure is using a barometer. And a barometer, this is a very simple barometer, exists of a pool of mercury with a tube inside there. Notice it says vacuum. And what that means is there's nothing inside of there. There's no air in there. There's nothing that would push back. So the amount of pressure that the atmosphere is putting onto this mercury, it's forcing the mercury into the tube. And if we measure that at sea level, it is about 760 millimeters, the distance that mercury is. And that's a pressure unit, millimeters mercury, comes from the barometer. And we have a bunch of conversion factors here. So we could say 1 atmosphere equals 760 millimeters mercury. We could say 1 atmosphere equals 101.325 kilopascals. We could say 760 millimeters mercury equals 101.325 kilopascals. So sometimes you'll see a big string of equals, and you just have to be able to use these as factors in order to make the conversions.
Just choose the two that you need. So in this case, we have nitrogen gas. We have a pressure of 452 millimeters of mercury, and we want to know what this is in atmospheres, and that's ATM. So we go to our conversion factors. We see that 1 atmosphere is 760 millimeters of mercury, and we cancel our units and convert the units. Oftentimes we do use atmospheres in a lot of our gases calculations.
So a scientist, last name Boyle, studied the relationship between pressure and volume of a gas and found that they were inversely related, meaning that as you increase the pressure on a container of gas, the volume goes down, and just the opposite. If we decrease the pressure, the volume would get larger. Now, this is only if the amount of gas and the temperature was held constant. So using this relationship, we can say that the volume is proportional to 1 over the pressure. Well, this can be rearranged to say that if we have a pressure and a volume, it'll be equal to a pressure and volume under a different set of conditions. So if we have 3 of these, we can solve for the 4th. So here's an example. We've got a sample of gas. It has a volume at a pressure. Now we're compressing this. So what do you think is going to happen to the gas, right? If we're increasing the pressure, we would expect a decrease in volume. And it's always good to think about these before you actually do your calculation. So we use this P1 V1 equals P2 V2, and we just solve for V2 in this case, and we get a smaller volume than the original, 0.139 liters.
One thing you want to make sure of, you want to make sure that your pressure unit on either side of the equal sign are the same, and your volume unit is also the same. So here's another law, Charles' law. He took a look at the relationship between temperature and volume and found that these are directly related. So as your temperature increases, your molecules are moving faster. They're having more collisions with the container, and the volume can expand. So as your temperature increases, your volume will increase as well. And then if you cool the gas, they'll move slower and have less collisions with the container, and it will shrink it. So we have this volume is proportional to temperature relationship. So if you set these if you compare one condition to another, then you have volume over temperature equals volume over temperature. So if you have a situation, well, we'll show you one right now. So here we have a sample of gas, we have a volume, and at a temperature. So it's a set temperature, and the gas then is warmed, right? It warmed under constant pressure, then we can calculate the new volume. So we're going to use this relationship, this Charles' Law's relationship of volume over temperature equals volume over temperature. And here it is. Be careful. Temperature must be in Kelvin for all of these calculations. So this problem gave the temperatures to you in Kelvin, but if they were in Celsius, you'd have to convert them first. So here we have, it makes sense that we have a larger volume at a larger temperature.
Avogadro also had a law that he applied to gases, and it's no surprise that he was concerned with the number of particles, right? You remember Avogadro's number. So what he realized is that the volume of gas is directly related to the number of particles. If there's no particles, no gas, there's no volume. If there's lots of gas, there's bigger volume. So it seems rather intuitive, but I guess it was a big enough discovery to make a law.
We need to make a discovery to make a law. So here we have volume over moles equals volume over moles. Because remember, the number of particles is the number of moles. Moles is a number. So we don't have just one set sample of gas in this circumstance. We have 0.25 moles of gas, and we have a volume, and we also have them at a set temperature. If we add more gas to it, we would expect the volume to go up. It's saying that it's at constant pressure, so that means that the container must be allowed to change its volume, and we can use Avogadro's law to calculate this new volume. So V over N equals V over N, and we can solve for our missing volume. And if we have liters on one side and we solve for volume, then we're going to have liters in our answer.
Always check those units. It's pretty common to put a little spin on the units. It'll ask for the volume in milliliters or something. So just keep an eye out for that.
All right, here's your practice. We have a converting between units for pressure, and then one of each of our examples here. So be careful. You might have to convert to Kelvin, and you might then have to convert between pressure units or milliliters and to liters.
Yeah, I see a lot of that in here, actually. So pause the video. This will take you a little while, but
it's good practice.
It is good practice. Give it a try.
All right, here's your answers, and hopefully you didn't get tripped up. These are to the correct number of significant figures as well, so make sure you go back and watch the significant figures video if you're unsure of how to do that. And that concludes this little lecturette. Thanks for watching, and always come back to the place to learn chemistry where you matter. Have a good day.